Welcome back to The Deep Dive, your shortcut to being well-informed. Today, we're embarking on a journey, really diving into the fascinating secrets of the D-block elements.
That's right.
Imagine a group of metals, so incredibly versatile, they're kind of the backbone of modern industry, but also sometimes a hidden environmental issue and maybe even key to future medical stuff. That's the D-block.
Indeed. These elements, yeah, they might just look like that block in the middle of the periodic table, but their properties are really, really captivating. We're going to explore what makes them tick, how they behave, and why they're just so crucial.
And our mission today, cut through the jargon, make it clear, give you the essentials on these chemical chameleons.
Exactly. We want you to get a feel for the trends and the underlying reasons.
We're using a great chapter from Shriver Atkins Inorganic Chemistry as our map here. We'll walk through the key ideas step by step. Think of it like a guided tour, making the complex stuff clear, no textbook needed right in front of you.
A solid plan. Where should we start?
Okay, let's unpack this. So, basics first. What exactly are D-block elements? You hear D-block metal and transition metal thrown around a lot?
Yeah, often together. But there's a useful distinction our source points out. D-block elements are just, well, geographically located in that central block. Simple as that.
But transition element, that's more specific.
Right. The official definition from IUPAC says a transition element is one that has an incomplete D subshell, either as the neutral atom or, importantly, in its ions.
So that's the key. It explains why group 12 zinc, cadmium, mercury are technically D-block because of where they sit.
Exactly. Positionally, they're D-block.
But non-transition elements, because when they form ions, like zinc 2 plus white substance, their D subshell is actually full.
Precisely. It's a neat chemical point. And within the block, we talk about the rows as series 3rd, 4th, 5 pen.
Like periods 4, 5, 6. And early versus late D-block just means left versus right side?
Yep. Early ones on the left, the late ones on the right. Simple geography of the block.
Okay, so why all the fuss? Why are they so important?
For versatility.
Right.
Absolutely. The source really hammers this home. They're workhorses in industry. They're vital in research. Think titanium in planes, copper wiring everywhere.
It's that ability to change oxidation states, isn't it? That chameleon thing.
That's a huge part of it. It's not just a chemical trick. It's why they're amazing catalysts. They can shuttle electrons around, make reactions happen that wouldn't otherwise.
Okay, so that utility must be linked to how we actually find them in nature, right? And how we get them out.
Definitely. There's a pattern. The harder metals on the left, think titanium, chromium, manganese, iron, round. They tend to like oxygen. So you find them as oxides, or in these things called oxoanions.
Like sulfates, carbonates, that kind of thing.
Exactly. Oxygen-containing anions. But then you move right to the softer metals, cobalt, nickel, copper, zinc, the platinum group.
They prefer sulfur or arsenic.
Yeah, sulfides or arsenides are more common for those. And this chemistry dictates how we extract them. Titanium, for instance, its oxide, TiO2, is super stable. Getting pure titanium is complex. It takes a lot of energy.
Right. It's not easy. But others are simpler.
Comparatively, yes. Chromium, manganese, iron oxides, you can reduce those more easily, often just using carbon, which is much cheaper.
And the sulfides, like copper or nickel.
For those, you typically roast them first, heat them in air. That converts the sulfide to an oxide. Then you reduce that. For really pure copper, you'd use electrolysis.
What are the others, like the platinum metals?
They're often tag-alongs. You get them as byproducts when you're refining copper and nickel. And gold. Well, gold is often just gold, found as the pure metal. Makes it easier to collect, relatively speaking.
Now, this ties into something really crucial from the source box 19.1 on toxic metals. It's not just about getting useful stuff out. Mining really stirs things up, doesn't it?
Oh, absolutely. Natural cycles exist, metals move around slowly. But mining and industry have massively increased the amounts of these metals circulating in the environment way above pre-industrial levels.
And even essential metals can be toxic in high doses, like copper and iron.
Right. We need them, but too much is bad. And copper actually becomes toxic much faster at lower concentrations than iron does. Part of the reason is its chemistry. Copper ions really like to bind to sulfur and nitrogen atoms.
Which are common in proteins, right? So they interfere with biological function.
Exactly. They mess with the machinery.
And the source stresses how the oxidation state is critical here. It changes everything about how a metal behaves in the environment.
Hugely important. Take mercury. Deep underground, mercury sulfide isn't very mobile. But bring it to the surface, expose it to air, it can oxidize to mercury sulfate, which is mobile, dissolves in water.
And metallic mercury vapor, Hg0. That's the really nasty one for breathing.
It is, because it's neutral, uncharged, it slips right through membranes, lungs, even the blood-brain barrier. Then inside the body, it gets oxidized to Hg, which causes damage.
But even worse is methylmercury, CH3Hg plus Te.
That's considered the most hazardous form. It gets absorbed easily from the gut, and it bioaccumulates. It builds up in organisms and moves up the food chain.
The Minamata disaster, a terrible example of that. Industrial pollution leading to severe poisoning through contaminated fish.
A truly tragic case study. It really highlights the potential consequences.
And it's not just local, is it? Mercury from, say, coal power plants can travel globally.
That's right. It gets into the atmosphere, travels long distances, and then rains down, potentially far from the source. It's a global contamination issue.
Okay, let's shift gears a bit. Physical properties.
Yeah.
What makes these metals behave the way they do physically? Melting points, density.
It all comes back to their electronic structure, how those d electrons participate in metallic bonding. The bonding strength actually peaks around the middle. Group 6, chromium, molybdenum, tungsten. They have just the right number of d electrons for really strong cohesion.
And do you see that reflected in melting points?
Absolutely. Alkali metals on the far left,
Yeah.
very low melting points. Then it climbs across the d block, peaks right there at group 6. Chromium melts high, tungsten even higher, ridiculously high actually, only carbon beats it.
And then it drops off again towards the right.
Yep, drops down, leading to group 12, zinc, cadmium, and of course mercury, famously liquid at room temperature.
Now, you mentioned something earlier. The lanthanide contraction. That sounds
Yeah.
intriguing. What's that about?
Ah, yes. It's a really interesting effect. You'd naturally expect atoms to get bigger as you go down a group, right? So 5D elements should be quite a bit larger than 4D elements in the same group.
Makes sense. More electron shells?
But for the elements after the lanthanides, starting with hafnium in the 5D series, they're surprisingly similar in size to their 4D counterparts directly above them, sometimes even a tiny bit smaller.
Smaller. How does that happen?
It's because of the 4D electrons that get filled in across the lanthanide series before you get to the 5D elements. These 4D orbitals are, well, they're not great at shielding the outer electrons from the increasing nuclear charge.
So the nucleus pulls the outer electrons in more tightly than you'd expect.
Exactly. It effectively contracts the atom size, hence lanthanide contraction.
And that has knock-on effects.
Big time. It doesn't just affect size, it increases ionization energies for those 5B elements. It takes more energy to pull an electron off. This is a major reason why elements like gold, platinum, iridium are so unreactive, so noble. They hold onto their electrons tightly.
Wow. So a subtle effect deep inside the atom dramatically changes how the element behaves out here in the world.
That's chemistry for you, quantum effects having macroscopic consequences.
Okay, let's dive into the chemistry proper. Oxidation states, this is where the D block really shines, right? All that variability.
It's definitely a defining feature. Let's look at the third series first. The group oxidation state, where the oxidation number matches the group number, like +3 for tandium in group 3, +4 for titanium in group 4, that's reachable for the early guys.
But it peters out.
Yeah, you don't typically see it beyond group 8. Manganese in group 7 can hit +7, but only with oxygen, like in permanganate, MnO4. Fluorine can't quite get it there. Oxygen's better at stabilizing those really high states, partly because it's smaller.
And as you go across the third series, those highest states become less stable.
They do. Chromate 6, manganate 7th, ferrite, they're all powerful oxidizing agents, meaning they want to grab electrons and go to a lower oxidation state. And that tendency increases from chromium to iron. The highest state gets progressively less happy.
What about the more common intermediate states, like +2?
Oh, the +2 aqua ions, the MOH262 plus ones, are super important in solution chemistry. Often colorful too, think blue copper sulfate solution. That's the Cu2 plus aqua ion.
Are they all stable in water?
Not equally. Vanadium-2 and chromium-2 aqua ions are actually strong reducing agents. They want to give away electrons. Iron-2 is weakly reducing, but cobalt-2, nickel-2, copper-2, they're generally pretty stable sitting in water.
And the +3 state?
More common on the left side, scandium, titanium, vanadium, chromium. Manganese really likes being +2 because that gives it a half-filled D subshell, which is stable. Cobalt-3 in water is a very strong oxidizer. Nickel a third and copper-3 aqua ions. Basically unknown.
Okay, that's across the third series. What about going down a group, say comparing third to fourth and 5 pins?
Here's where it gets interesting and maybe a bit counterintuitive. For groups 4 through 10, the highest oxidation state generally becomes more stable as you go down the group.
Really? More stable for the heavier elements? That feels backwards compared to, say, main group element.
It does, doesn't it? But
Yeah.
it's a key trend here. Compare manganese, which struggles to make MnF4, with rhenium just below it, which easily forms Re7. The heavier elements are more comfortable in those high oxidation states.
So tungsten compounds like WF6 aren't strong oxidizers like CrVi compounds are.
Exactly. WF6 is quite stable. Molybdenum, PCOS, and tungsten are very stable states for those metals.
But here's a weird one from the text. How easily the metal itself oxidizes doesn't always match the highest state it can reach.
Right. That's another subtlety. Iron metal rusts easily, mainly forming Fe2 or Fe3, but you can't force iron to 8th. Yet ruthenium and osmium below iron are much harder to oxidize. Initially, they resist acids, but if you hit them hard enough with oxygen, they will go all the way to the +8 state, forming ReO4 and OSO4.
Okay, that's complex. Let's talk structure. How do these trends affect the shapes and sizes of compounds?
Well, ionic size generally decreases across a period, as you'd expect. But for the N2 plus ions, there are some bumps and wiggles in the trend. It depends precisely which orbitals have electrons in them and how they interact with the surrounding ligands, the atoms bonded to the metal.
And the heavier elements, being bigger, can fit more things around them.
Generally, yes. The 4 and 5-beat elements often show higher coordination numbers. They bond to more ligands compared to their third cousins, especially with small ligands like fluoride.
And we saw that covalent character increases with oxidation state, too. Low states tend to be ionic solids, high states more covalent, maybe even molecular liquids or gases.
Like OSO2 being an ionic solid, but OSO4 being a volatile molecular substance, a clear trend.
Now let's talk about the posh end of the E block, the noble metals.
Ah, yes, the lower right corner. Silver, gold, and the platinum group metals. Ruthenium, rhodium, palladium, osmium, iridium, platinum.
Why are they so unreactive, so noble?
It comes back to a combination of factors we've touched on. Strong metallic bonding within the metal itself, and those high ionization energies, partly thanks to relativistic effects and the lanthanide contraction for the heaviest ones. It's just hard to rip electrons away from them.
Which is why they're good for jewelry and coins. Copper, silver, gold. Okay. The coinage metals don't react with simple acids.
Right. But even nobility has its limits. Aqua regia can dissolve gold and platinum.
That famous mixture. How does it work again?
It's a clever combo. Concentrated nitric acid is the oxidizer. It pulls electrons off the gold atom, but that's not enough. Concentrated hydrochloric acid provides chloride ions, which immediately grab the newly formed gold ions, like Au3+, and form a stable complex ion, AgFeOl4.
So the chloride pulls the gold into solution, preventing it from just sitting there, like teamwork.
Exactly. A chemical 1-2 punch, oxidize, then complex.
But this nobility kind of vanishes after group 11, right? Group 12, zinc, cadmium, mercury, they're much more reactive.
Abruptly so. They tarnish in air, react with acids. The strong metallic bonding seems to weaken, and the electron energies shift, making them easier to oxidize. The magic wears off.
Okay, let's look at some representative types of compounds. Metal oxides seem like a good place. They're everywhere.
Absolutely. Oxygen is common, so you get a huge variety. From simple ionic things like the third metal monoxides, MnO, FeO, NeO, some of which are useful, like MnO can scavenge oxygen.
All the way to those covalent molecular ones we mentioned, like OSO4, toxic, volatile, but useful in organic synthesis for adding two OH groups across a double bond.
Right. Cis dihydroxylation, a very specific tool. Then you have oxidocomplexes where oxygen acts as a ligand. Think permanganate, MnO4, or chromate, CrO422. Very common for metals in high oxidation states.
And things like the vanadilyl ion, VO2 plus oxide.
Yep, vanadium-4 often forms square pyramidal structures with a very short vanadium-oxygen double bond. That short bond influences the bonding on the opposite side, the trans influence.
And then there are those amazing cage structures, the polyoxymetallates.
Oh, yeah. POMs. These are fantastic clusters, usually formed by early D-block metals in high oxidation states like vanadium V, molybdenum, tungsten 6, metal atoms linked together by shared oxygen atoms into complex polyhedra.
They sound complicated but visually striking, used in catalysis.
Yes, potential catalysts, even some medical applications being explored. They can incorporate other atoms too, forming heteropolyoxymetallites like that PMO 12O4O3 example with phosphorus inside a molybdenum oxygen cage.
Okay, moving on from oxygen. Sulfides.
Metal sulfides. Sulfur is softer than oxygen, prefers softer metals. Sulfides are generally very insoluble. You get simple monosulfides, but also disulfides.
Like fool's gold, FeS2. iron pyrite.
That's a classic disulfide. Importantly, it's considered iron 2, bonded to a disulfide ion, S2-2. That's different from something like molybdenum disulfide, MoS2, which is molybdenum with simple sulfide ions, S2. MoS2 has a layered structure, useful as a lubricant.
And there are sulfide clusters, too, relevant in biology.
Hugely relevant. Iron-sulfur clusters, often cubane-like structures, FRS4 cores, are absolutely essential components of many enzymes involved in electron transfer, like in nitrogenase, which converts nitrogen gas to ammonia.
Incredible. Finally, what about metal-metal bonds? We touched on bonding within the bulk metal, but bonds between metal atoms in distinct compounds.
Yes, this is a really rich area, especially for the heavier D-block elements. Many compounds exist where two or more metal atoms are directly bonded to each other, sometimes with incredibly short distances. These are often called metal clusters.
And the bonding can be complex. Sigma, pi, even delta bonds.
That's right. The overlap of d orbitals allows for multiple bonding. Sigma, two types of pi, and even a delta bond where all four lobes of two orbitals overlap face-on. This can lead to quadruple bonds, like in the famous Re2Cl82 ion.
Whoa, 4 bonds between two metal atoms.
And remarkably, even quintuple bonds, 5 bonds, have been made between chromium atoms in specific compounds.
That's wild. And these bonds are stronger for heavier metals.
Generally, yes. Metal bond strength tends to increase as you go down a group, 4 or 5 bits stronger than third. That's why clusters and MM-bonded compounds are much more common and stable for the heavier D metals like molybdenum, tungsten, rhenium, osmium. Think of compounds like MaCl2, which actually exists as clusters of 6 molybdenum atoms, Ms and Al6Cl142.
So much variety.
Well, that was quite the journey, wasn't it? From where these D-block elements live in the Earth, through their extraction, their unique physical quirks like the lanthanide contraction, the huge range of oxidation states,
And their nobility, or lack thereof, the different types of compounds they form, right up to metals bonding directly to other metals. It's a lot.
it really is. But hopefully you can see the threads connecting it all. How the electron configuration, those d electrons, are really the key to understanding their behavior, their size, their bonding, their reactivity, their stability.
Absolutely. It's amazing how that one section of the periodic table holds such diverse and important chemistry, from gold jewelry to industrial catalysts to essential biological components, and yes, even environmental toxins like mercury. Understanding the trends really gives you an appreciation for their impact.
So what's the takeaway for you, the listener? It means you now have a kind of mental map, a framework for thinking about a huge chunk of inorganic chemistry. You can start to predict properties, understand why certain elements behave certain ways, see the connections.
Yeah, it's not just memorizing facts for an exam, right?
Mm.
It's about understanding the why behind the chemistry of the world around us, from steel structures to the trace metals in our vitamins.
Precisely. It equips you to make sense of it all.
And thinking forward, it definitely raises a question. Given how incredibly versatile these elements are, and we're still discovering new things about them, what's next? What new catalytic magic or maybe undiscovered biological roles might be waiting in the D block?
That's the exciting part, isn't it? The potential is still enormous. New materials, more efficient catalysts, maybe even understanding diseases better.
Definitely something to think about. Thanks for joining us on this deep dive.
Thank you.